Hello student, welcome back. Today we will going to study a new topic, that is oscillation, as per the new syllabus. Below are the contents of the topic that we are going to study in today's lecture. Start the topic oscillation. Oscillations is very common and interesting phenomenon in the world of physics. Like oscillations of a simple pendulum, oscillations of a clock pendulum, swinging of a swing, vibrations of a musical instrument like guitar, violin, etc. These are the examples of oscillations in our day-to-day life. Now, what do you mean by the oscillatory motion here? Or it is also called as the vibratory motion. So, what is oscillatory motion or vibratory motion? Oscillatory motion is a periodic motion in which a particle repeatedly moves to and fro along the same path. Got it? Oscillatory motion is a periodic motion. It is a periodic motion in which a particle repeatedly moves to and fro along the same path. For example, we can see the example here. Here, there is a bob of a simple pendulum. This is the position O. This is the point O here. And this is the point E. This is called as the point of suspension, and this is the center of gravity of a bob. So OA here, mean position, or it is also called as the equilibrium position. Now, if this bob is released, this bob is moved here in the position B. Now from B to A again, and then again this bob is moved here from A to C, and then again it goes from C to A. Here, when this bob moves from its equilibrium position from A to B, then from B to A, again it moves from A to C, and then C to A. It completes one oscillation. The path covered here in one oscillation, that is AB plus BA plus AC plus CA. So, here the bob of a simple pendulum completes one oscillation. Such an oscillation takes place again and again. So, this is a periodic motion also. Means, what do you mean by the periodic motion here? Periodic motion means any motion which repeats itself in equal, we can say that here, definite interval of time. Interval of time. This is the periodic motion here. And this bob performs here the periodic motion. And here any oscillatory motion is a periodic motion. Focus here. Any oscillatory motion is a periodic motion. But not all the periodic motions are the oscillatory motion. What I can say that here all the oscillatory motion are a periodic motion. All the oscillatory motions are the periodic motions, but all the periodic motion are not an oscillatory motion. आता तुम्ही म्हणाल की इथे मॅडमनी असं का लिहिलेलं आहे, तर सगळ्या प्रकारचे ऑसिलेटरी मोशन्स या पिरियडिक असतात. कारण आपण जे एक्झाम्पल्स घेतलेले आहेत जसं oscillations of a simple pendulum, this is a periodic motion because here this bob moves repeatedly again and again to and fro along the same path. This is a periodic motion. Again, in the example of clock pendulum, the pendulum oscillates to and fro along the same path. Swinging of a swing. This boy swings to and fro. That is also the example of oscillatory motion. Vibrations of a musical instrument like guitar, violin. In these all cases, these all are the oscillatory motions. Means that is the periodic motion. So I will say that here all the oscillatory motion is a periodic motion, but all the periodic motions are not oscillatory motion. Why all the periodic motions are not oscillatory motions? Because as we have already seen in the first topic, circular motion, when the electron is revolving around the positively charged nucleus, then this electron is revolved like this along the circumference. It is a periodic motion, no doubt, but it is not an oscillatory motion because this electrons not completed oscillations here. Here, all oscillatory motions are a periodic motion. Here we can say that all oscillatory motions are a periodic motion. Means in periodic motion the particle repeatedly move along the same path again and again. This is oscillatory motion, or it is also called as the periodic motion now. In this chapter, we have to calculate here velocity, displacement and acceleration. And to calculate these three values, that is velocity, displacement and acceleration, we use the functions sine, cosine, and that functions are known as the harmonic functions. That functions are known as the harmonic functions. And that's why this oscillatory motion is known as the simple harmonic motion. Now, when the path is a straight line, if a path is a straight line, suppose this is the mean position, or it is also called as the equilibrium position. This A and B are the extreme position. The particle is moving here first O to B, and then from B to O, and again then it is moving from O to A, then again it goes from A to O. It completes one oscillation here. This periodic motion, this path is a straight line path. So, this motion is known as the linear simple harmonic motion. Linear simple harmonic motion. And as we see earlier example, if the path is an arc of a circle, if the path is an arc of a circle, then this motion is known as the angular simple harmonic motion. In place of linear, we use angular simple harmonic motion. I will repeat here. If the path is linear, that means it is a straight line, then the particle moves along a straight line path. So this motion is known as the linear simple harmonic motion. This oscillatory motion is known as the linear simple harmonic motion here. But if the path is an arc of a circle, then this motion is known as the angular simple harmonic motion. In this chapter, we will study the linear simple harmonic motion. Explanation of linear simple harmonic motion. Explanation of linear simple harmonic motion. Now, this linear simple harmonic motion is explained in the following example here. Here, we take a mass spring oscillator. Suppose in this figure, this is a rigid one. This is a rigid one. And this is a spring. And here, another end of a spring, there is a rectangular block. Here, another end of a spring, there is a rectangular block having the mass m. Show this example here. Here, we consider a spring. This spring is attached or fixed at one edge from a rigid support. This is rigid wall. And the other end of a spring is fixed to a rectangular block. This is a block having mass m. And this block is placed here on a horizontal surface. This block is placed in a frictionless horizontal surface. This is a frictionless horizontal surface. Means without any friction, we can move this ball. We can pull this ball right side or left side. Okay. Now, here, this spring is at relaxed position. Now, in this position, the spring is in the one end of the spring is fixed to a rigid wall and the another end of the spring is fixed to a block of mass M. And this is the relaxed position of a spring. Here the force equals to 0 here. Also displacement equals to 0. Means here the spring is at relaxed position. No force is here. Hence force equals to 0. Displacement is also 0. This is shown in this figure here. Now, if the spring is stretched now we can stretch this spring. Here in this figure, this is a rigid one. Now, this spring is stretched here. So, this block, rectangular block, is pulled at right side here, having the mass M. This rectangular block in this figure, here this spring is stretched now. If the spring is stretched, then the length of the spring get increased. Here this is a displacement takes place here. The block is moved. The block is moved at right side here when the spring is stretched. So there is a displacement takes place and that displacement is denoted by x here. So the displacement is x here. We can show here this displacement. Yes, this is a displacement x here. And when this spring is stretched here, then the force is inward side. The force acting is inward side. And that force is here k into x. Here negative sign is there. Negative sign indicates that this force and displacement are oppositely directed. It means when the spring is stretched, जेव्हा आपण त्या स्प्रिंगला ताणून धरतो तेव्हा त्या स्प्रिंगची लेंथ वाढत आहे. ते डिस्प्लेसमेंट आपण डिस्टन्स कव्हर x ने दाखवलेलं आहे. आणि जेव्हा त्या स्प्रिंगला आपण ताणून धरून राहिलो आहे आणि हा ब्लॉक ज्याचा मास m आहे तो ब्लॉक आपण राईट साइडला ओढतो. राईट साइडला पुल करत आहोत. So the force exerted inward direction and the displacement is outward direction. So force and displacement x is like that and the force is like that, inward side. So the force and displacement are oppositely directed here. Now, shown in below figure. This is a rigid one. Now the spring is compressed now. Now the spring is compressed. This is a rectangular block having mass m. This is compressed, extremely sorry. This is a relaxed position. This is stretched position. And this is compressed position. Now in compressed position, This block of mass n is pushed left side here, and the spring is now compressed. Spring having the property of elasticity means the spring gets its original shape and dimensions. Here the spring gets compressed and the block moves towards left, that is towards equilibrium position, so that the force is now moving. The force is now moving outward direction, and the displacement is now. The displacement is now minus x here, because here this force is at outward direction and displacement is on inward direction. Means displacement is moving towards mean position. Hence, force and displacement are oppositely directed. This is the spring mass oscillator. This figure shows spring mass oscillator. For the explanation of linear simple harmonic motion, I will again repeat the spring mass oscillator system from this figure. Here, in this figure B, there is a relaxed position. Means the spring is at relaxed position. Here, there is a rigid wall. Means the spring, one end of the spring is attached to a rigid wall here, and the other end of the spring is attached to a rectangular block having mass m here, which is placed on a frictionless horizontal surface here. Now, in this relaxed position, the force F equals to 0. Also, displacement x is 0. This is the explanation of figure B. Now, here in this figure A, the spring is stretched. If the spring is stretched, then the length of the spring get increased. Means here the displacement takes place. So this is the displacement here, x. And here we pull this block at right side. This block is pulled at right side, so the displacement is at right side. But when the spring is stretched, the force is at left side. That is, in inward direction, it goes to the equilibrium position. Hence, here force and displacement are oppositely directed, and this force is k into x. Here, negative sign shows that force and displacement are oppositely directed. Displacement is directed at outward and force is directed at inward here. Now, in figure C, there is a compressed position. The spring is at compressed position. In this compressed position, the block is now moved towards left side. So, here the displacement is minus x. Means block is moving towards equilibrium position. So, the displacement is at left side here. So, we put here minus x. And if this block is compressed, the force is at outward direction here. So, again, force and displacement are oppositely directed. And from this consideration, from this above consideration, here in OH et al, what is linear simple harmonic motion? harmonic motion is a linear periodic motion. Linear periodic motion in which a restoring force or acceleration, a restoring force or acceleration is always directed towards its mean position, and its magnitude म्हणजे त्या restoring force magnitude, its magnitude is directly proportional to the displacement, directly proportional to the displacement of a particle from its mean position. So from this consideration, the definition of linear simple harmonic motion are here. The linear simple harmonic motion is a linear periodic motion in which a restoring force, this restoring force, it is always directed. It is restoring force or acceleration, because this is accelerated towards mean position here. So, a restoring force or acceleration is always directed towards its mean position, and its magnitude is directly proportional to the displacement of a particle from its mean position. Okay. Now, from this definition here, we can say that here the magnitude of this restoring force is directly proportional to the displacement of a particle from its mean position. So, if F is the force and X is the displacement here we can say that here this F is directly proportional to X. So here we can retain as here how this F equals to minus Kx. How this relation comes here, we can solve here. We will solve here F directly proportional to X. So F equals to K into X. Here K is the force constant. Here we put the negative sign. Here the negative sign shows that force and displacement are oppositely directed. The meaning of this negative sign here, the force and displacement are oppositely directed. Hence, here the restoring force becomes F equals to minus Kx. This is the formula of restoring force here. Now, we also say that here restoring force or acceleration. Now, here the acceleration of a block. The acceleration of a block here, we know that force equals to mass into acceleration according to the Newton's second law of motion. Force equals to mass into acceleration. So, acceleration of a block here. Acceleration A equals to F by m here. So, we put here the value of F. So, put the value of F force. So here this above equation becomes acceleration. A equals to फोर्सची व्हॅल्यू इथे आपण इक्वेशन 1 मध्ये -kx घेतली. So acceleration becomes now -kx upon here m. So here k is the force constant and m is the mass of a block, which is also constant. So here acceleration A equals to minus k upon m into x. This bracket shows constant here. K is also constant. This is the force constant here. K is the force constant here. So K is also constant and M is also constant. So this bracket shows constant. So the acceleration is directly proportional to x. Acceleration is directly proportional to displacement here. Negative sign shows that acceleration and displacement are oppositely directed. This is the acceleration here. Acceleration of a ball, and this is the restoring force. Now equation 1 shows here restoring force and equation 2 shows here the acceleration. Now from this equation 1 we can calculate the value of this k, that is force constant. From equation 1, the force constant K equals to, we take here magnitude. I use the word here magnitude. जेव्हा आपण magnitude घेत असतो तेव्हा ही negative sign इथे काढतो. म्हणजे इथे force constant K हा F by x होईल. That is force constant K is restoring force per unit displacement here. Now the formula of this force constant K is F by x here. Now the SI unit of that force constant, the SI unit of force constant is Newton per meter. Why it is Newton per meter? Because here the force is measured in Newton, per the displacement is measured in meter, and its CGS unit is dyne per centimeter. Now we can calculate here the dimensions of force constant. This is the SI unit, okay? That is Newton per meter here, and the CGS unit is dyne per centimeter. Now the dimensions of force constant K are K equals to F by x. We take here dimensions in standard form, that is length, mass, time, L and G, and the dimension shows here in square box. Here this force means mass into acceleration here. So the dimensions of this force are L1, M1, T minus 2 here, and the dimensions of displacement is L1. Now here L minus 1 is here, 1 minus 1 here 0, L0, M1, T minus 2. This is the dimensions of force constant. So The dimensions of force constant becomes now L0, M1, T minus 2. This is all about the linear simple harmonic motion. In this linear simple harmonic motion, from that mass, spring mass oscillator, how we can calculate here force, acceleration, what is force constant here, what is the SI unit of force constant, CGS unit of force constant, and the dimensions of the force constant. Here is all about the linear simple harmonic motion. These formulas are very important in the numerical purpose, also for the multiple choice questions. In the next lecture, we will see the differential equation of linear simple harmonic motion. So keep studying and happy learning. Thank you so much.